Good afternoon. My name is Jamal Abdalla. I'm professor of civil engineering at the American University of Sharjah. With me, Dr. Hawileh. He's also professor at the American University of Sharjah. Ahmed Mirghani, he's an engineer who graduated from the American University of Sharjah with a master's degree. Myself and Professor Rami, we supervised his master thesis. The title of the presentation today, as shown, is Bond Stress and Behavior of Interface between Untreated Aluminum Alloy Surface and Concrete. The presentation outline is shown. I will start with the introduction, and problem statement, and the objectives, research objectives. Background and literature review will be followed by experimental program, experimental results and discussion, conclusions, and references. Introduction. Well, we all know that strengthening and retrofitting of reinforced concrete structures are one of the hot research topics within civil engineering, and it calls the attention of many researchers and practitioners due to a number of reasons. Well, there are many design errors that need to be corrected by strengthening members. There is the number of aging structures is increased. Corrosion and deterioration of steel mechanical properties also happens due to environmental reasons. Creep deformation, changes in structural usage, building functions that may result in increase in dead load, life load, and others. Design code modifications, usually design codes evolve over time, and therefore some new requirements will emerge, and then the building has to comply with the new requirements. Members sometimes may add something to the building or remove some of the elements that changes the load path, and therefore some of the members need to be strengthened or so forth. Well, in some cases, maybe members receive some damage due to either earthquake or other reasons, and therefore they need to be retrofitted. And sometimes we'll be faced between two difficult choices: either demolish the building or strengthen it. And of course, strengthen it is cheaper than demolishing the building. The pictures in the left here shows typical externally bonded reinforcement for beams and slabs and columns. Okay. You can see here they're using the carbon fiber reinforced polymer. I think these are plates, and they can strengthen also masonry, and as shown in the back there. Of course, as I mentioned, extensive research has been conducted in the last 3 decades to evaluate the performance of strengthening materials. Of course, different strengthening techniques have been used to increase the axial, flexural, shear, and torsional strength and stiffness of structural members. One of the most widely used technique is the use of steel and fiber reinforced polymer as externally bonded reinforcement. Steel kind of lost its popularity due to many reasons, because it is susceptible to corrosion and then other kind of shortcomings it has. Well, FRP emerged as the most widely used external bonded reinforcement, and this is due to many advantages it has, and of course it also has some few disadvantages that problem statement. Well, the use of steel and FRP and other materials already has a great impact on strengthening and repairing, retrofitting of structures. Okay. Of course, they have some shortcomings. Okay. What we are proposing here is using a new material, which is aluminum alloys, as that has some advantages over the other two materials that have been used, which is the steel and the FRP. So if we look at the steel, the steel has the disadvantages is that susceptibility to corrosion, and it has the weight heavy. The advantage is tactile, and it has a lower cost, and in between it has flexibility and it has the strength, but in the middle. The CFRP, the carbon fiber reinforced polymer, the advantage is that it doesn't corrode, it's lightweight. The disadvantage is that the failure is brittle, there is no ductility. a little bit costly, and this is inflexible, especially the plates. It's difficult to use plates, for example, in some situations. And of course, one of its disadvantages also, it has a high strength. It's higher than steel, most of the time. Aluminum, if you see, it has more green. It has a good resistance to corrosion. It's lightweight. It has ductility, high ductility, and the cost could be just like steel or lower. And it's easy to deform or easy to form that compared to steel or plates or CFRP plates. Of course, the strength is not as high as steel or not as high as the CFRP, but sometimes you don't utilize the full strength in the other cases. Okay, so that was just shown there, summarized in this table, showing that the aluminum alloy could have some of the advantages that overcome some of the disadvantage or the shortcomings that we have in the current material for externally bonded reinforcement. Okay, so what explore the viability of using aluminum alloy plates as a newly externally bonded strengthening material. Okay. Of course, in order to do that, we need to assess the ultimate load and to study the modes of failure between the aluminum alloy and the concrete interface, and how they are being affected by the aluminum alloy surfaces, treated or untreated, bonded length, and the concrete strength. Background and literature review. Well, we said the structural member reinforced with external bonded reinforcement consists of, first of all, you have the concrete material, the member, and then we have the adhesive, and then we have the externally bonded reinforcement, whether steel, FRP, or aluminum in this case that we're going to see. Well, the external bonded reinforcement improve, of course, the original tensile strengths provided by the steel bars, and therefore that will contribute in enhancing the strength and the stiffness of the member. Of course, in order to do that, there must be some kind of shear transfer between the externally bonded material and the element that you want to strengthen. And there is usually an adhesive or epoxy adhesive in between, or the layer in between the two of them. So that shear strength that in between the two need to be evaluated in order to ensure the effectiveness of the strengthening. There are many factors that affecting that bond between the external bonded reinforcement and the element that need to be strengthened. We're not going to cover all of them, but the one that ticked by green and the one that's we're going to touch on them. The effect of the concrete compressive strength, the effect of the bonded length, and the effect of the surface treatment on the bond between the aluminum and the concrete. There are other factors as well, but they are not considered here. The experimental in the experimental program, we have material properties, specimen details, and instrumentation, and then the test matrix. I will go a little bit fast on this. Okay, we have different materials that's involved in this. Well, the concrete, the aluminum alloys, the epoxy adhesive, and the strain gauges that used to instrument the specimen and measure the strains. In particular interest here in the aluminum alloy plates, we use specifically AA aluminum alloy 5083-H111, what has a tensile strength of around 300 megapascal and modulus of velocity is around 70 gigapascal. The rest of the things are we casted different samples: concrete, cubes, cylinders, and prisms. Here the mold we use for the prisms. Here are the cylinders and the cubes, large and small. Here is the testing setting for the cubes and for the cylinders. And here is a specimen which is ready to be tested using a direct shear test. The specimen details and instrumentation. Here is the dimension of the specimen, the aluminum plates with the dimension. The adhesive thickness is ranging between this and this. And here is a typical sketch of a specimen that's been prepared. And then after that, the setting you see here is for holding the specimen for direct test. And here you see the picture of it, details of the specimen, instrumentation of the specimen, mounting of the specimen into the rig for the testing, and then putting the rig into the tensile machine in order to carry out the direct shear test. this is a test matrix. There is around 32 prisms that have been developed. The strength, concrete strengths is we have 20, 30, 40, and 60 megapascals, and the bonded length is 50 millimeter, 100 millimeter, 150, and 20 millimeter, as is done for each strength. Okay, and we did 2 elements for each of the members, so we end up with all that number of elements that need to be tested. So we test all, and some of the results, showing a sample of the results. Here the typical result of one of the tested element, which is has a concrete strength of 60 megapascal. P is for plain aluminum, and L4, that means this is L number 4, which is the bonded length. L4 is basically the 200 millimeter, the largest length we have. And here the figure shows you the different behavior. Well, the first one on the top left show you the shear stress versus the distance from the loaded end, and you can see that the shear stress increases up till a certain length, and then after that starts to decrease. The second one show you the relationship between the slip and the distance from the loaded end, and the slip is maximum at this end and approaching 0 when it's approaching the other end. And then you have the bond stress slip shown here, and then we have the strain distance, because we have strain gauges that have been mounted on the system and measuring the strain, and you can see the variation of the strains as we go from one point to the other. And the one in the top right show you the load strain relationship, and the load is applied, what will be the corresponding strain in the 4 different strain gauges. And then the last one in the bottom right corner shows you here the load versus the extension of that particular member. So this is for one element which is of 60 megapascal concrete strength, and the length is L4. I'll just comparison show you another element, okay, which is something slightly similar, but this length is L2. L2 is 100 millimeters. So this is half of the bonded length of the previous one. So you can see how the behavior changes as the length change, and as the material property, also material strengths of the concrete also change. Last one is for even a lower strength, 20 megapascal, and the length is 4, which is the bonded length. And you can see the different curves that are showed for the stress versus distance, stress versus slip, load versus extension, load versus strain, and so forth. Okay, there are different failure modes, but most of the elements, which as we call it plain plates or without any treatment of the surface, the failure is very much by debonding. And the exception of few of them, especially those which have high strength concrete, they show not debonding and a little bit of delamination, but not much. So debonding is the most dominant failure, which is telling me that the aluminum surface as is not very good in providing high bond stress or shear stress between the aluminum and the element that you need to strengthen. So something needs to be done about the surface. And actually we have other experiments we did in which the surface of the aluminum has been treated, and that shows big difference in terms of the shear resistance after the treating of the. Okay, here I show you some of the tests summarized in this is, for example, the concrete strengths and bond strengths and its effect on the ultimate load. And you can see that sometimes you see a trend, and sometimes the trend is not there, because the debonding is a premature failure, so it doesn't really tell you the whole story sometimes, but some of it is show you some pattern, for example. Here is the summary of the effect of the ultimate of the comparison of the ultimate load for the plane surface of the aluminum and the surface that has been roughened, and you can see how much difference it made when we have the surface of the aluminum get treated, the blue ones here, which is R is for roughening the surface. The average strength of the material of ultimate load change drastically. You can see here. This is for the maximum stress for the surface which is plain or untreated. Comparison of the maximum bond stress for the material when the surface is treated and when the surface is not treated. So obviously the difference is big between the red and the blue. So obviously, in order to use aluminum as an externally bonded material, you have to treat. It seems like running out of time here. I will jump here to the to some of the points here. Point number 3: the ultimate load capacity and the maximum bond stress based on the average values increased by almost 400 times and 300 times for the load and for the maximum bond stress when you have the surface untreated, when you have the surface treated. So obviously that's the main conclusion coming out of here. To use aluminum as an externally bonded material for strengthening any member, you have to treat the surface, and that will make a big difference in terms of the resistance. Of course, the failure modes also will change if the surface changes. These are the